Hello and welcome to everybody on my YouTube channel Cloud Fitness. So today we are going to talk about some Delta Lake optimization techniques that we can use to query our data, right? And let's go to some key highlights that we have on what we are going to discuss today and what are the optimization techniques actually. So the very first thing when you talk about a delta lake, delta table, in that case, the very first thing for optimization is partitioning. You should have a proper partitioning over your data to, have your data query faster, right? And the second thing that is compacting and reordering. This together actually is comes under file management operation because the partition files which you create from the step 1, those partition file management is actually handled by compaction, compacting and reordering. So when you talk about compacting, it is done by optimize, and reordering also I'll talk about it in my video. The third one is data skipping. So data skipping is essentially something which is done by all the databases, and we are going to discuss this here as well. And the fourth one is caching, and we also know that how much important caching is when you talk about the performance. So let's go ahead and see about the partitioning. So when you talk about partitioning in Spark, your data gets partitioned. It gets it gets partitioned into subset files, some subset of Parquet files. So for regarding partitioning also, you need to make sure that whenever you partition the data, you always choose a low cardinality column. Never go for a high cardinality column, like if you have a employee table and you have an employee ID in it, and you kind of know that there are 1,000 records and you'll have 1,000 employee ID, so then definitely employee ID is not the option to partition over, right? So always go and try for the low cardinality column. It will give you much better results. And then remember one more thing, that by default try to have at least 1 GB of data in each partition. So it should not have that you have given such a column in partitioning that your Parquet file has just one record and the other Parquet file has 1 TB of data. It should not be like that. So each partition must have at least kind of 1 GB of data and should be evenly distributed, so there should be no data skewness while partitioning. So also let's go ahead and see on the Databricks portal how we can do partitioning, although I have explained all these things in my previous videos as well, somewhere not as a part of optimization technique, but yes, definitely we have used partition by. So I've zoomed my screen as well. So as you can see, I've created this data frame from a file. I have 5 columns: sepal length, sepal width, petal length, and petal width, and species. And in command 2, I'm actually trying to repartition the data. I've explained about repartitioning in my past videos. If you haven't checked partitioning versus collace, go ahead and check that video as well. So when you talk about this, I am trying to repartition the data. The reason I'm repartitioning it into 3 is because just for the demo purpose, basically, I have only 150 records, so there is nothing to kind of optimize. But this is how you partition on the data frame. This is how you partition by, and I have also written species. So species is the column I'm trying to partition by. I know that I have only quite few values in the species. I have only 3 kinds of species. It is a low cardinality column I'm trying to partition by. Species, I'm trying to save it as a delta table. Now when I have saved it as a delta table, I am trying to see how it looks like. Now, if I'm trying to do an ls over the table, you can see here I have the partitions created. So these are the partitions. These are the different species that I have: Setosa, versicolor, and Virginia. So these are the species. Now let's go inside each partition and check what's happening. So if you go inside Setosa, so this is basically the partition. I'm just trying to see through what's going inside that particular partition. So you can actually see that I have 3 partitions because I have already repartitioned it, right? So I have these part files. So these part or these Parquet files are actually your data. This is your data, and let's this is basically how you do partitioning. So let's go ahead and move to the slide, and then I will explain you what I have for you in terms of compacting and z ordering. So when you talk about compacting, this is the second technique which should come in your mind while working on Delta Lake. So this compacting, what does it do? Let's say you have a streaming job which copies batch of files, or which does some kind of operation on your Delta table, but the kind of data that is written is very small. So in that case, you will have lot of small files generated over time, right? And this will actually cause issues. In that case, compacting comes into picture because it reduces the small number of files within a partition into a set of optimal size of a files. That is called compacting. Now it is done through a keyword called as optimize. I'll go through that as well. And the third thing that should come to your mind is z ordering. So this compacting and z ordering are file optimization techniques. So when I say file optimization techniques, these are happening on your partition, inside your partition, on your Parquet files, right? Because your small number of files are Parquet files which are getting generated within a partition, right? So this is where your compaction comes into picture, and z ordering also is done within the partitions. So how z ordering is done? Z ordering actually tries to co-locate similar type of data, right? In case let's say you have a particular UZ order by, let's say UZ order by dates. So when you try to z order by date, it will internally try to place all the records of 1st Jan 2021 nearby, so that while reading it is actually very fast. So this is what compacting and z ordering is all about. Now when you talk about compacting, it happens to optimize. So that is the keyword. So when you try to compact it, you will actually write optimize and you will write the delta table name, or this is how you will actually optimize the whole table. Now in case you have a very large table and you don't want to optimize the whole large table, you can go only and optimize only a subset of the table, which is done by adding predicate like this: optimize table name, where column and any kind of condition that you have, right? So based on this particular condition, you can actually optimize only a subset of data. Now let's go ahead and let's go to the uh, Databricks and see how you can optimize. So now I already have a delta table, right? So since I'm using a Python notebook, I'm using %SQL magic command over here, and then I'm trying to do optimize, and I'm trying to optimize the whole table over here. So when I'm optimizing the table, and you can see the output over here, the number of files added, the number of files removed, right? This is how optimization is being done here, right? So if I have some files which are kind of very small files, and they will actually be, all the records will actually be compacted into a larger file. So this is how your optimize work, and you can actually see all the statistics over here, which are actually pretty useful statistics, and these statistics are stored in your transaction log. So if you go above, I'll show you. Probably you have transaction log whenever you create a delta table. Let me show you. So guys, this is where your delta transaction log is created. So this was my delta table, and I have these partitions, and I have this delta log. So this is where my actual, I actually wanted to show you over the UI. So this is where my whole um, uh, this data which I showed you over here gets stored. How many number of files were added, how many number of files were removed. So all these things about your latest file is actually placed in that transaction log. And now this is your optimize, this is your compaction. Now this transaction log is actually used by Z order. So when you say Z order, what happens is Z order will actually get the statistics from the transaction log, and it will try to co-locate the data because it will have minimum maximum value, right? If you can see over here, it has minimum 1204, maximum 1436, whatever these statistics are. So based on these statistics, it will actually try to play co-locate the data. So that is what Z ordering is all about. And then we have data skipping. So when I talk about data skipping, this is the fourth option that we are going to discuss. So data skipping is as normal, as you see in any other database. So this data skipping is automatically present in your Delta Lake because of basically partition files. So when you have partitions, you have partition parquet files. So Spark already knows, or your Delta Lake already, it already knows where your data is. So it already tries to read only relevant data. So that is how your data skipping is anyway present. There is no specific configuration that you need to keep while data skipping. However, if you want to leverage the best of all the worlds, you want to leverage optimize, you want to leverage Z order, you want to leverage data skipping all together, then this is the command for you. So you can basically optimize table where, and then you can place your conditions, and then you can Z order by the column. So the best thing will always be to have a column with high cardinality inside the Z order. I'll explain Z order more in detail. So this is something where you are actually getting the best of both worlds. You are trying to optimize the table. You are trying to compact the files, any extra small files. You are trying to compact it through optimize. And then you have your partitions as well. And then you have your Z order as well, right? And you have your data co-located. And now when you have this Z order and you have Z order and optimize all together, then data skipping even works pretty well. So just wanted to make sure that you know this. And before moving on, I like to mention few points regarding data skipping. So when you talk about data skipping, by default, if your table has thousands of the column, it will by default take the first 32 columns to check the statistics. So in case you have 1,000 columns, it will only take statistics of 32 columns by default. You can definitely go ahead and change this number using data skipping num index columns in the notebook, or even at the cluster level. You can change this number, but this is not something that you would like to do. So the best thing is, if you want to skip data based on the statistics of a particular column, try to keep that column, try to alter the table and keep that column in the first 32 columns, right? This is the best way that you can do data skipping. And then coming on to the Z ordering, because I wanted to talk about this in more detail. So when you talk about the Z ordering, as I told you, it is co-location of the data. Now this diagram is basically illustration of how your data is co-located. It is multi-dimensional basically, right? And so for example, even if you see the command over here, optimize table events is the table where there is a specific condition, and then Z order by event type. So try to keep the column in Z order which has more cardinality, so you can actually try and co-locate all those columns easily. And it is always better to have any column which you are using often, which you will be using often, and you have high cardinality as well. You can keep it in the where clause and try to use the same column in the Z order, then it will give you perfect results. Also, one more thing I wanted to mention about Z ordering is that Z ordering is idempotent. So when I say idempotent, it basically means that if you do Z order second time, right, it is not going to give you the same result. So let's say you did Z order by a particular column, and this is how your data got co-located in the first block. But when you z order on this again on the same column, it will internally try to change the position of the records, right? It will actually, it might change it, the data will be still co-located, your similar data will be co-located, but the location will be changed. However, this will not affect your query performance at all. So this is something that we need to, make sure that we know that z ordering is idempotent. And when you talk about z ordering, so I talked in the beginning regarding these file management optimization, z ordering and compaction. So when you talk about z ordering, it is idempotent because when you uh, try to change, when you try to z order again on the same column, internally it will try to um, relocate the data basically. And when you talk about compacting, doesn't matter, you can run it 1,000 times, it's going to give you same result. Now let's move ahead and also talk about the delta cache. So this is the fifth thing, that fifth optimization technique that we wanted to talk about. Now this delta cache, I think everybody knows how important it is. It basically, tries to store your data temporarily in the cache so that your reads are more efficient. Delta cache is, however, different from Spark cache. They both operate on different levels altogether. Delta cache and Spark cache are completely different. Delta cache is actually on SSD. So delta cache, it will pull all the files. It will retrieve the data, whenever you're reading, and whenever you are reading or writing, it will actually take the delta cache and locate them on worker node itself. But when you talk about Spark cache, uh, it is all an in-memory operation, or the way you specify it. And delta cache is automatically enabled. You don't there is no specific option where you have to go and write something like delta cache enable. It's not like that. But when you talk about Spark cache, you have to go and manually change the code, right? You have to write like df dot cache or df dot persist, you do the storage level, at which level you want to cache. So you have to manually write that. And this thing is not with the delta cache. Delta cache is already automatically available, but in case you want to disable it, yes, you can go ahead and change the configurations in the notebook, or even at the cluster level you can change the configuration flags over there. But that is not something obviously you would like to do. And there is one more thing that you know delta cache will definitely help you to accelerate your delta reads. And yeah, and both of them are lazily evaluated. So I hope everybody knows about that the Spark is lazily evaluated. So until you perform any action, until you actually it is enabled, cache is enabled, but until you actually read the data or write the data, it doesn't work. So you have to perform an action to use the delta cache. So let's go back and quickly revise what we have discussed. So these are the optimization technique. The first one is partition. So you have to partition on a column which has the lowest cardinality, which does not have a very high cardinality. That will work well with partitioning. And once you have partitioned the data, it enables faster read operation and as well as write operations. And when you talk about inside partition, now once you have already partitioned the data, compacting and z-ordering comes into picture. Compacting happens with the optimize keyword, right? With optimize, you can actually compact the smaller files, and with z-ordering, you can co-locate the files. When you talk about data skipping, it is automatically enabled. You don't have to do anything to enable it. It is automatically enabled because you have already done partitioning of the data. And using that partitioning, it kind of does data skipping. Also, if in case you want to leverage the best of data skipping, then enable partitioning, enable compacting, enable z ordering on your data, then automatically data skipping will be at a much faster pace. And then you talk about caching. When we talk about cache, you have your Delta cache. It is also automatically enabled. You don't have to do anything to you know enable it, and it happens on SSD. So these were the key highlights from today, and this is what I wanted to discuss for now. And thank you guys, thank you so much for watching this video. And in case you have not subscribed to my channel yet, do remember to subscribe to my channel, and remember to post a comment in case you have any doubts or you want me to make video on some other topic. Thank you so much.